In this video, we present our paper elucidating the hierarchical nature of behavior with masked autoencoders. Behavior is naturally organized in hierarchies, as illustrated, for example, by Tinbergen's 1942 model of the reproductive drive in stickleback fish. In our work, we aim to uncover such beautiful hierarchical structures in behavior. We adopt the hierarchical notation from Anderson and Perona, where movements, representing fine-grained movements, nest within actions, and those actions in turn form part of broader activities. To uncover the hierarchical structure of behavior, we focus on learning embeddings for action segmentation. Our contributions are twofold. First, we introduce a hierarchical transformer model that learns embeddings across multiple scales. Second, we present two new benchmarks for hierarchical action segmentation, SHOT-7M2, which includes the three previously defined levels of behavior, and HBabble, which provides labels for both frame-based and sequence-based actions. We introduce SHOT-7M2, a synthetic dataset designed to capture the hierarchical and compositional behaviors of a basketball player across various action classes. The dataset provides rich, multi-scale annotations that span 14 movements, 12 actions, and 4 activities. You can see in these visualizations how behaviors can happen at the same time and break down into smaller units. In addition to SHOT-7M2, we extended the Babel dataset into a hierarchical action segmentation benchmark, comprising about 38 hours of motion sequences. It includes two scales, sequence level and frame level annotations. For instance, you can see here a shake action segment, which is composed of finer actions like arm movements, standing postures, and hand movements. To learn and infer hierarchical levels of behavior in a self-supervised way, we rely on masked autoencoders, which have proven to be highly effective models across various modalities, including video data. Specifically, we build upon the Hierarchical model, which incorporates a hierarchical structure into the MAE architecture and has been successfully applied to both images and videos. The core of our model is based on how we construct an explicit hierarchy. The input level is defined by the way we tokenize a given pose trajectory. For instance, for a mouse's pose trajectory, we can learn an embedding for every single key point for entire body parts, or we can represent a single token by the full pose. This spatial granularity is complemented by how much temporal information is included in each token, represented here as T. In the forward pass of the model, tokens are progressively merged either temporally, spatially, or spatiotemporally. This results in a latent hierarchy that captures different levels of granularity. Our HBehave MAE model builds on a standard transformer architecture, with the addition of merging stages after certain encoder blocks. The decoder is a straightforward one-layer transformer block, which either fuses embeddings from all encoder scales or decodes embeddings from the final encoder stage. The pre-training objective is a L2 loss applied to the masked-out parts of the input trajectory. To maintain consistent fusion during the forward pass, we employ random masking based on the largest scale of the model's hierarchy. Our model surpasses previous state-of-the-art methods on the Maybe 22 challenge, a benchmark for representation learning of mouse behavior. Both HBehave MAE and its non-hierarchical counterpart, Behave MAE, achieve strong performance across all subtasks while being trained exclusively on raw pose data. On the SHOT-7M2 dataset, HBehave MAE shows strong performance across all three behavioral categories. The lower levels in green are particularly effective at encoding movements, while the higher levels, in blue, excel at actions and activities. Additionally, HBehave MAE maintains high performance across all categories, whereas the non-hierarchical Behave MAE is limited to a single scale, resulting in inferior performance. On SHOT-7M2, HBehave MAE outperforms Behave MAE on all three behavioral groups while showing interpretable performance compared to the relatively flat curves of Behave MAE. We observe the same trend on HBabble, where HBehave MAE better balances overall performance with lower layers better decoding frame-level actions and higher blocks sequence-level actions. Additionally, our model shows robustness with respect to hierarchical depth. Early layers specialize in smaller movements. Later layers better capture activities, while actions peak before the final layers. To wrap up, MAEs are effective models for pre-training on skeletal data without the need for extensive feature engineering. Hierarchical MAEs can enhance performance compared to non-hierarchical models by better balancing different behavioral levels. The embeddings of HBehave MAE explicitly correspond to their respective levels in the hierarchy. For more information, please check out our paper and feel free to visit us at Poster Booth 212. We look forward to discussing our work with you.